Hey, thank you. Thank you, everyone. Can you hear me well all over? Yeah? Raise your hand if you can't. Okay. Good. So that's me. The title, which is not, where's my clicker? Yeah. Well, the title is a bit of a lie because I'm going to tell you about zero knowledge on steroids called secure multi-party computation and what you can do about it. And I have tailored this especially to an audience of Web3 developers. Good. So let's start with some kind of flavor. So suppose I'm a brilliant data scientist and I want to work with a brilliant pharmaceutical corporation that is doing tests on groundbreaking medication, but they don't have a really strong data science team. I am a super strong data scientist, but I don't really have the access to the patients and to the medicine and so on. If we trusted each other, everything is good. If we sign NDAs, that's really nice, but that has all kinds of problems with compliance and so on. What we really want is for me to keep my private information, the part that has the I with the cross on it. You'll see this throughout the talk. That's the part that I want to keep private. And the corporation wants to keep the patient data private, but we want to gain all the benefit as if we were divulging all our information. That's the kind of tasks we're going to talk about today. Another example, Tinder. I am speaking to Amanda. We want to know whether we both swipe right, but I don't want Amanda to know what I swiped in particular. And Amanda also wants to keep her swipe private for me. We want to get, so right now we use the Tinder servers. So Tinder is a trusted intermediary that does the computation of the end function of whether we're both interested. But we want to really decentralize it, and the question is how to get that functionality without trusting a central party. Voting is the same thing. We want to compute who won the election, but all the votes need to be kept private. And an application you may know very well, sending money. Right now, if I use Bitcoin, my public key is posted online as well as the amount of money I transferred, right? But if we use a bank to do a transfer, the bank doesn't divulge anything. When I transfer money to someone, I don't want anyone on the internet to know anything about that I passed some money around and so on. So trusted intermediaries give us privacy right now, assuming we trust them, but the Bitcoin network doesn't quite. There is a solution for this, right, that you may well know, called Zcash. In Zcash, people can transfer money to other people without anyone knowing that anything interesting has happened beyond that someone transferred some amount of money to someone else. So Zcash does solve this, but what happens with Web3 applications? So what we're going to talk about today is privacy technology. We're going to talk about provable privacy, privacy that you know is secure. It's not just heuristic. It's cryptographically provable. And I want to focus specifically on private computation, not private communication. I'm going to argue there's a huge difference that we're going to talk about. So the agenda will be, I'm going to tell you why you should care about privacy on the blockchain, and in particular about private computation. We're going to say a little bit about how cryptographers implement private computations and what the primitives look like and how you should think about this. We're going to talk about some really great futuristic applications, and then I'm going to take it down and tell you as Web3 developers what you should be thinking about if you want to make your applications private. Okay, a little bit about me. I'm Elad, a computer scientist turned investor. I did my postdocs with the people who developed this science and turned it into technology, including in Aarhus University, the place where this was first deployed. So couldn't shut up about it since 2010, told everyone this is the future, zero knowledge and secure multi-party computation is going to change the world, unlock huge business. No one cared until the couple last years, people did start to care. This technology has been starting to be democratized and make it into the market, exactly in time for me to become an investor in Berlin and start my own VC, Berlin Innovation Ventures, which invests in algorithmic startups, very early stage. If you're developing anything around zero knowledge or anything else algorithmic, come talk to me later. So I think this will be a huge value unlock coming from these private computation technologies. So let me start to convince you that you should really care about privacy, even if you're not a bleeding heart and you don't really think that privacy is a huge value. So let's start by arguing that blockchain privacy is inherently broken. If you use your wallet to pay for a pizza, and then you use your wallet, the same public key, to pay for a bag of weed, then the cops can come, ask the pizza salesman where did they deliver to, and come arrest you. Right? That's the way that Bitcoin works if you use the same public key twice. You may say, well, I never use the same public key twice. I use mixing. Well, you have to use it twice, once to get the money and once to give out money, to send out money. But suppose you only use it twice. You're super safe. You use mixing networks. Apparently, that's not good enough, right? I mean, there's even a Coursera course about how to de-anonymize Bitcoin. And there's these companies that do chain analysis, for example, to prevent, detect, and investigate cryptocurrency money laundering, fraud, and compliance violations, because clearly that's the biggest problem in the world. What I'm reading when I read this is, oh, your Bitcoin transfers are not actually secure. If some motivated enough analyzer wants to find out who you are, they will do so. The real problem is that we have promised privacy. Right? If you ask people who know about Bitcoin what Bitcoin is, they'll tell you it's a private way to send money secretly. And the problem is we've been promising something we can't deliver, and that's going to end up biting us in the ass. So I could tell you there are solutions. Use Zcash, use Monero, use Corda. But what about your Web3 applications? We've also been promising that Ethereum is private. What are the solutions to that? Well, I'm going to argue that private computation and not private communication, importantly, is really important for your Web3 application. Suppose you're a dApp developer and you really want to decentralize Uber. Then how will you do that? Uber is a really complicated business logic. You need to preserve reputation. You need to calculate how much someone pays for their drive, and so on. So because of that, you need to, the way you'd naturally implement Uber on the blockchain is to post all of the private information on the chain, in the blocks. And you need to do that in the clear because you have to compute stuff from it. For example, the reputation change is a business logic, and therefore things need to be posted in the clear. That means that if I'm trying to spy on your users, I'm going to manage to spy on them very well. I'm going to see Donald Trump took a shady ride at 2 a.m., and I'm going to see that because you need to compute reputation changes and money and stuff like that. With private communication, you can't hide this data and still get the business logic. But with private computation, you can. And with private computation, the blockchain, the block will look like the one on the right, saying everything is garbled except the actually actionable changes like reputation change and so on. So I'm going to argue that even if you don't care about privacy at all, and if you think privacy is dead, then you really should care too. You might argue the press has said that millennials don't care about privacy and that privacy is dead. But that's not actually true. Millennials don't care about privacy as much as the older generation does, but they still care. They wouldn't post their DNA online on their Facebook account, I would hope, or their browsing history on their Facebook account. So obviously, everyone cares about privacy, but privacy is weaker than it used to be. The interesting thing is that if we really find a way to secure the privacy of users in our dApps, we're going to get people to share much more information, both end users and also corporations and businesses that are right now stopped by compliance, GDPR and stuff like that, from sharing a lot of data. And the insight is that the more data you get people to share, the more positive some value is created. Right? So privacy and privacy tech is really good for all of us because it fosters collaboration. That's why I don't like to think of it as privacy tech, but rather as collaboration tech. In a perfect world where everything is computed privately, we would have lots and lots of positive sum collaborations, and that's good for everyone, even for those who don't care about particular issues of privacy. Okay. So before going to talk about how cryptographers implement this technology, I want to kind of straighten out the buzzword zoo that we're all seeing. So the private computation that we'll talk about today is stuff like zero-knowledge proofs and secure multi-party computation. Those are the basic primitives we'll talk about. There's a whole different area of cryptography called private communication. That's the stuff we're kind of more familiar with, like public key cryptography and proxy re-encryption. And the way to think, and these are completely different types of technology or science. One of them, private communication, communication was started in the 70s by people who dress like the people on the right. These are Rives, Shamir, and Adelman. And the other one, private computation, was started in the 90s by people like Shafi. It's very important to remember that these are very different types of science. And we're also not going to talk about other privacy technology like IP spoofing, differential privacy, and so on. So we're going to concentrate on the leftmost side. Now, let me tell you a little bit about how cryptographers achieve privacy on the blockchain or private computation in general. And first of all, I need to define what I mean when I talk about private computation. What does this actually entail? So here's the definition of the strongest primitive for private computation, and it's kind of the simplest to explain as well. It's called secure multi-party computation. This originates in the 80s with the work of Yao on the millionaires problem. So this was introduced, let's say, 82, and it started about 20 years of research. Still ongoing. So the primitive is defined as follows. You have n players that want to compute a joint function of their inputs. So each of the players have a private input xi that they really want to keep private. That's their, where they're going to, riding to, and their DNA, and so on. So the player number I wants to keep their input xi private, but they all want to collaborate on computing a joint function f of their inputs, and they want to all get the output y. Now, each player may only learn, this is the cryptographic definition, and in the next slide we'll talk about how to actually think about it and define it. Each player may only learn what their input is that they started with and what the output is, and they may not learn anything about any of the inputs of the other players, even if some of the players are malicious and are really trying to collaborate and cheat and spy on the other players. No one is allowed to learn anything else. Okay? Now, the amazing theorem that was proved around the 80s and early 90s is that no matter, there's various versions of this theorem, but the general gist is that no matter what your function f is computing, no matter what your business logic is, this is doable using a protocol, and it only needs to assume some cryptographic assumptions and have a polynomial time overhead, which is reasonable, and that polynomial is improving with the years. So this is getting more and more efficient. So amazingly, it's the strongest thing you could imagine. No matter what you're trying to compute, we can compute it while keeping the privacy of the players. So that's the mind-blowing part that I think enables, and will enable a lot of value unlock. So in particular, if your function that you're computing is an auction, so each of the players has their bid, and you're trying to compute the maximum function, which is who bid the highest, then you have a protocol where all the players communicate, and no matter if they're trying to cheat or not, you're going to compute the maximum of these bids, and the only thing the players will learn is their own bid and the maximum of the other bids. Okay, so I should tell you about how this thing is defined, the red thing, may only learn. How do we argue about what someone learns from a protocol and doesn't learn from a protocol? It sounds really complicated. So I'll tell you how cryptographers view it. Suppose you're a cryptographer and you have a suggested protocol for secure multi-party computation, and it's a great protocol and you think it's super safe. How do you prove it's safe? Well, you look at the real world in which you operate on the left, where Alice and Bob, I'm just assuming 2 players for simplicity, it works for any number of players. You have Alice and Bob that communicate with each other, and Bob might be replaced by some demon that is trying to mess with the protocol and cheat on Alice and learn what X1 is. Then you imagine, for a second, you would be in the ideal world. In the ideal world, there's another player, Judge Judy, who is completely trusted and keeps everyone's privacy. And you imagine the simplest protocol imaginable, where Alice sends her input to Judy, and Bob sends his input to Judy. Judy computes the output and sends it back to the players. If you look at the protocol on the right, it satisfies all the properties we wanted. It computes the function, and the only thing Alice can learn is X1 and the result, no matter how much she's trying to spy on Bob. So the only thing we need to prove is that the protocol, that your protocol on the left works the same as the protocol on the right. And the way that computer scientists do this is by reduction. What they do is that they assume that there's some adversary that breaks the protocol on the left, and they prove that by construction they can change it to an adversary that breaks the security or the privacy on the right, because the right protocol is secure almost by definition, then the left one must be secure as well. So it's a proof by reduction, and we'll come back to this because this is a really great way to think about decentralization. We'll come back to this at the end of the talk. So I would love to show you how such a protocol is implemented, but we don't have much time for this. There are simple explanations. Come ask me in the Q&A later. So I'll show you how a much simpler protocol for a simpler task is done. So let's talk about zero knowledge again. Zero knowledge is the primitive where I try to prove something to you without telling you anything about how I'm trying to prove a claim to you without telling you anything beyond that the claim is true. So here's a classic example. Where's Waldo? Suppose you run a business and your business really benefits from finding Waldo in pictures. So this picture has a little Waldo somewhere in it, and you really want to find it, but you don't have a good algorithm for this. I come to you as a consultant, and I say, I have the best Waldo finding algorithm, trust me. You say, I don't want to trust you. Can you find Waldo in this picture? I tell you, listen, I don't want to do free work for you. This is my livelihood. So you see, we have a conflict in collaboration. We both want to collaborate, but we don't trust each other. Well, zero knowledge to the rescue. I have a protocol for proving to you that I can find Waldo in this picture without showing you how I did it or where Waldo is. Here's how we do it. So I ask you to turn around. We put the big picture on the floor. I ask you to turn around. And then I take a huge cardboard cutout, and I put the cardboard cutout such that only Waldo is shown in the picture. And it's so huge you don't know where the picture even started. So you can't find where I put the cardboard cutout on the picture. So you look, I ask you to turn back around. You look, you say, oh, you really find Waldo. Then I ask you to turn back. I take the cardboard cutout away, and that's it. So I prove to you that I can find Waldo, but you have not learned anything about how I do it, and you have not learned anything about where Waldo is in the picture. This comes from Kid Cryptography, a collection of really simple protocols, cryptographic protocols. So my point here is to show you how I can prove something to you without teaching you anything beyond the correctness of the claim. SMPC is, of course, a much more complicated thing, but it relies on the same thing, arguments about knowledge. Okay, and this is coming to industry. Kedit and Enigma are implementing zero-knowledge proofs and secure multi-party computation on blockchain systems, and there are many more projects like this. Basically, the whole field is getting democratized. So if private communication was democratized starting in the 90s with PGP, so originally only the president of the US could talk to the president of Russia over secure communication. And then it came to the army. Eventually, now we all have this in our phones, and we all can communicate privately. The same will happen with private computation. It's only a matter of, let's say, 20 years or so. So this is coming, and the only question is, what do we do with it? So what was done with it until now? So the first application was in Aarhus, Denmark, in a university that has, importantly, a really good game theory group and also a really good crypto group. So they came together and wrote a system, SMPC-based system for auctions of sugar bits. I won't tell you much about it. There's a really great paper about the first application of this. But this is also used for spectrum auctions. So when militaries release cellular frequencies, cellular operators want to buy this, but they don't want to tell each other how much these cellular frequencies are worth. So you design an auction where the highest bidder wins, but the bid of each cellular operator is kept private. So it's a mix of game theory and cryptography in order to create positive sum business value for the cellular operators and for the state that gets the money from the auction. And by now we have Zcash and other such systems. But what I actually want to talk about is the future. So imagine you're going into a time machine and you're emerging in 2040, and you look around and you say, how is private computation used? Let me show you two applications that I think we'll see. The first is ad auctions. So these are kind of the futuristic applications, although, interestingly, when I started talking about this, it was futuristic. By now, there's edX, which claims to do this. So this is coming to field pretty quickly. The premise is the following. So right now, ad auctions are run by Google and Facebook. You're an eyeball, right? You have some demographic information, your gender, your age, and so on. Google auctions you to the highest bidder, and they don't reveal much to the advertiser beyond your demographic information. But we are trusting Google and Facebook. We kind of have to, and they know a lot about us. We want to run this with secure multi-party computation, decentralize the whole ad market, And then your ads will be served in a decentralized way, keeping your entire privacy, keeping the privacy of who you are and what your demographic information is, but still showing you the highest bidding ad and doing the payment to the publisher. So ads, SMPC ads are, auctions are already a big thing, as we said in the last slide. But interestingly, these ad auctions will be really interesting because with privacy comes more data sharing. So you can all of a sudden incentivize people to share not only their demographic information, but also their browsing history, their bank records, their medical records, their DNA. So I can advertise to you based on your DNA. I'm not saying this is the world I want to live in. I'm saying this is the world I will live in. So we're going to see decentralized ad auctions that reward the user for sharing the data, so they get a kickback, and advertises very, very efficiently based on all of your private information. If you don't like that application, I have a good one, a much more noble one for you that should make both the libertarians and the communists in the room equally happy. This is algorithmic redistribution of wealth. So I personally believe that the nation state can't go away very, very soon because the nation state has a coercive power that is really useful for maintaining welfare. Systems that allow you to opt out of them have a spiral of death. The people who with the most to gain by opting out, opt out, and the thing spirals into no one participating. So the nation state isn't going away too soon. The problem with the nation state is not so much its coercive power, which is bad, but it's that it uses it in such a dumb way. So if you think of taxation, taxation law is dumb. It's legacy code. If you look at tables for how you compute the amount of tax that you pay, there's clearly something wrong with it, right? Because it's designed for accountants to compute, for you to be able to check at home, and for legislators to pass. So corporate tax is dumb. All of these systems are like rule-based systems. They don't make sense. What should this work like? Well, we have really good algorithmics for running factories, for controlling all kinds of feedback, complicated feedback systems. So the same algorithm or the same kind of trends in algorithms that are used to control factories efficiently can be used also to control countries, to optimize for stuff like social welfare, for GDP growth, and so on. You'll need to mix in some game theory, like in auctions, or mechanism design to make the players, all of us, truthful. We need to mix in some economics to figure out what's best for people and so on. But you can design these algorithms and note that they don't have to be optimal. They don't have to be perfect. They have to be better than the legacy systems we're working on with right now. I think between us in this room in a day, we can devise a better machine learning and econometrics algorithms than we use right now to redistribute wealth. The problem is that unlike machines where you can attach a sensor and send all of the data to the blockchain, humans care about their privacy. And these algorithms should really care about my medical records, DNA, and so on. So we need to make these systems preserve our privacy and still get all the business value. So zero knowledge and secure multi-party computation will be really necessary for these upcoming systems that I think we'll see in like 10, 20 years. More than that, I think in general, we have a big governance problem by the fact that all of our governance methods are based on legacy systems. So our governance is based on voting every 4 years, on very simplistic rules of voting and so on. And I think we'll see crypto governance based on SMPC that makes governance much more efficient. So I want to tell you a bit about practical issues as Web3 developers. How do you use these systems? So to use SMPC, your biggest, if you want to take your dApp that is right now not preserving privacy, and you want to preserve privacy because you're designing, for example, an Uber, how do you do this? Well, what you do is you design your system in the system on the right where there's a Judge Judy, and then you apply an SMPC compiler of sorts to transfer it to the left. And this is not a trivial task because you need to define your function f very carefully. So what SMPC promises you, if you define your function f to actually concur with how you think about the privacy of your users, this will carry to a decentralized setting. And the challenge is defining f and making sure the privacy is kept over time, even when you apply f many times. Next, people come and ask me, is SMPC too slow? And the answer is, for most of these applications, it is. But it won't become faster using a Moore's law, I think, is possible, but it only will happen as soon as we ask for it and deploy SMPC in our systems. And what's the solution for this? Well, there's a new solution, relatively new, called Trusted Execution Environments. That's how Enigma does it. So Enigma lets you have privacy-preserving smart contracts where the developer chooses whether their privacy will be kept using trusted execution environments, which is the part of the processor that even the owner of the processor presumably can't look at. It's not 100% secure, but it should be fine for now in the interim years until we get a Moore's law for private computation that makes SMPC algorithms as fast as Zcash, for example, as fast as Starks, or as fast as Zcash implements zero-knowledge proofs and so on. So if you build it, they will come, and this will be faster. Finally, will the users trust you, right? Because it's really hard to tell the users, listen, there's this magic moon math that preserves your privacy no matter what. So in the same way that it would be really hard to convince someone to get on a big chunk of steel and tell them they'll move through continents. The reason users do this is because they've seen others do it, and they've done it themselves, and nothing bad happened. Similarly, we put our credit card on the internet. Something that would be completely crazy in the 80s became commonplace now because we see this little green lock, and we say, oh, this won't be divulged, just like planes don't crash very often. So with regulation and normalization, there will come adoption. It's only a matter of time. So ask me more about this. There's also a talk I gave online just about adoption. To conclude, 4 major lessons. Private computation is not the same technology as private communication. A lot of people kind of pretend like it is, but you really need to be aware of both and that they're not the same thing, and that private computation won't, communication won't give you all the benefits you need to preserve actual privacy. Web3 requires private computation. There's a massive design space of private applications to explore over the next 10 years, and to apply this in your Web3 dApps, what you need is to figure out what your function f is, and then talk to some smart cryptographers or read stuff online. But basically, if you have a function f, no matter what f it is, there will be private computation for it. There's a lot of further reading. I'll post these slides online. And just to conclude, so Yuval Noah Harari has this really great claim in his great book, Sapiens, where he says, listen, the thing that separates humans from animals is not their ability to use language, because some animals have that, and not their ability to use tools, because many animals actually have that. It's our ability to have shared myths that allow us to collaborate together, share myths like God, like money, like the nation state, things that would disappear if we didn't all believe in them. And that's a way to collaborate on massive projects. Similarly, Ethereum is a collaboration technology that allows us to trustlessly obtain trust and to collaborate together, but Ethereum is missing one, or other blockchain systems are missing one big thing, which is privacy. Adding privacy technology into blockchain systems will allow us to collaborate much better and to get, the new pyramids of the 21st century. Thank you.